All right, so in talking about acid-base equilibrium, right, it's very much similar to chemical kinetics and solution equilibrium. It's always going to be products over reactants, right? KEQ is products over reactants. It's the same thing here, right? But instead now we're talking about acids and bases. So there's a couple of different acid-base theories that you need to be aware of. There's actually three, but we'll go over two of them right now. The first one is Arrhenius acid-base theory. In Arrhenius acid-base theory, an acid is a substance that when you dissolve it in water, increases the concentration of hydrogen ions, right? Which you already knew that. And a base is a substance that dissolves in water and gives you more hydroxide ions, right? That's what a base is. Well, that's all good and stuff, right? But the problem with the Arrhenius acid-base theory is that it doesn't describe most reactions, right? Because not all chemicals have hydroxides, right? Not all chemicals have hydrogen ions, right? Well, really, this is really the Bronsted-Lowry acid-base theory, right? Is designed to address the fact that not all bases have hydroxides in them, right? Not all bases have hydroxides in them, and so Bronsted-Lowry acid-base theory is one of my favorite acid-base theories, and I affectionately call it this. I call it BLAP, right? That's how I remember Bronsted-Lowry acid-base theory, BLAP, right? See, B for Bronsted, L for Lowry, A for acid, B for base, and then T for theory, BLAPT, right? And so for BLAPT, an acid is a proton donor, right? And a base is a proton acceptor. So now, when we're talking about acid-base theory, all we need to worry about is whether there's a proton being donated or there's a proton being accepted, right? And it still addresses the same thing Arrhenius base does, because there's no hydroxide ions even mentioned in Bronsted-Lowry acid-base theory, but the hydroxide ions, remember, have a negative charge. And so what can they do? They can accept a proton, right? So it still fits in with Arrhenius acid-base theory, even though we don't even talk about hydroxides in the BLAPT. Okay? So, one more time, acid-base BLAPT, an acid is a proton donor, a base is a proton acceptor. So here's your next question. A Bronsted-Lowry acid is a what? All right. Still waiting for three more people, one more person, one more person, one more person. Yes, there we go. That one person has signed in. And then we can take a look here. The vast majority of you here answered B, which is a proton donator. Absolutely. A Bronsted-Lowry acid is a proton donator, right? It is not a proton acceptor. That is a Bronsted-Lowry base, right? So you have to be able to make sure that you can tell the difference between something that is a proton acceptor and something that is a proton donor, right? And a Bronsted-Lowry base is a proton acceptor. A proton donor is a Bronsted-Lowry acid, okay? So let's talk about water as a proton acceptor, right? Acceptor, like reptar, right? When hydrogen is formed, or when a hydrogen ion is formed in water, it does not exist by itself for very long, right? It instantly forms a hydrogen bond with water. So here we have water, right? And then you can think of this hydrogen ion right here as just some acid from like hydrochloric acid or from like sulfuric acid or whoever, right? And almost instantly what happens is that this hydrogen ion here will hydrogen bond to the water like that, and that gives us the hydronium ion, right? So for the rest of this chapter, you won't see me ever refer to the hydrogen ions by themselves, they will always be referred to as the hydronium ion. And that actually should look familiar for you because you did this guy in Vesper. You built it in the Vesper lab. Remember that? Right? You built it in the Vesper lab, right? So just remember that this is called the hydronium ion. Hydrogen. That's what hydronium ion. Yes, that is called the hydronium ion, right? And I will definitely be talking about that a lot, right? I won't ever refer to it as a proton by itself anymore. I will most of the time call it a hydronium ion, right? All right, so here we just have some examples of some more hydrogen bonding with hydronium ions, with more hydronium ions. So here's three hydronium ions connected to each other with hydrogen bonding. Here's a hydronium ion right here, just hydrogen bonding with a water molecule. And so those are the kind of species that you'll see when you have water being a proton donator. Yeah.
Can you explain why it's hydronium? The name?
Yeah, that's just what they named it, hydronium ion.
Okay.
Yeah, the hydronium ion. Like, I don't think there's actually any specific reason it's called the hydronium ion, but that's just the name of.
Okay.
If you have this right here, right, the H3O plus like that. If you have the H3O plus, it's always called the hydronium ion, right? There may be something special, and that's why it's called the hydronium ion. But things that have water in it, or oxygens, or hydrogens, are always weird. Like, there's if you get you can get like things like deuterium, or what's another funny one with hydrogen? There's a whole bunch of funny names with hydrogen that they haven't figured out yet. Yeah. No, there isn't. I don't think there is. I don't think there is a. I don't think there is a naming system like rule for hydronium. But you'll find that water just is very special. It's very different, and so people just give it its name, right? Like, for example, its IUPAC name for water is like dihydrogen oxide, right? But nobody calls it dihydrogen oxide. Everybody calls it water. So, yeah. But then you get hydrogen peroxide, which is H2O2. So you're like, so why you call that hydrogen peroxide, but you call water water? But anyway. So let's talk about in more detail about the Bronsted-Lowry acid bases, right? Bronsted-Lowry acid bases. We have here, right, an acid must have at least one removable proton, one acidic proton to donate, right? And a Bronsted-Lowry base must have one non-bonding pair of electrons to accept a proton, right? So here, like I was talking about before, we have hydrogen chloride gas, right? And what it can do is that it can dissolve itself inside in some water, right? And we know for a fact that water has oxygen in it, and this oxygen has the two lone pairs right here, right? And so since it has those two lone pairs right there, the proton that's from the hydrogen chloride gas can come over here, right, and add on to the water to make the hydronium ion right here, right? So your products from this reaction, hydrogen chloride plus water, is going to be the chloride ion and the hydronium ion, right? Notice that we still have neutral charges on both sides. That's that rule, that thermodynamics rule or law, charge conservation, right? And so it's neutral over here, and it's also neutral over here because one's negative, one's positive, right? And so it's actually, just so everybody's clear, it's actually this right here, the hydronium ion, that makes something acidic, right? So we call things like hydrochloric acid an acid, right? But really, hydrochloric acid is hydrogen chloride gas, and it's not an acid, right? Or act like an acid until you mix it with some water and it becomes a hydronium ion. That's what makes it acidic, right? So by virtue of the fact that you see HCl there, don't think that that's immediately an acid, right? It's got to go and make the hydronium ion for it to become an acid. Okay. So, see, here we go. What's different about water? Because I was just telling you how water is so different. People treat it so differently. It acts different too. It's the only substance I know that has its most dense part at 4 degrees Celsius, and then it gets less dense when it gets colder. Most things, when you make things colder, it gets more dense as it gets colder, right? But water, for some reason, is most dense at 4 degrees, and then when you make it even colder, it gets less dense, and that's why ice actually floats, because you freeze ice at lower than 4 degrees, and that's why ice floats in water, because it makes ice is less dense than water because it's past 4 degrees Celsius. Isn't that weird? So weird. So weird. Most things in nature, if you make it colder, it gets more dense. But water, exact opposite. It's crazy. Absolutely crazy. All right. Um, lost my train of thought. Oh well. Water can act as a Bronsted-Lowry base and accept a proton from an acid, like on the previous slide. But it can also act as a proton, donate a proton, and act as an acid, as seen below. This makes a water what we call amphiprotic. Amphiprotic, right? So here we have the ammonia, right? And ammonia is actually normally a gas, but you can throw it in some water and then it becomes aqueous, right? And then the water here is what acts like an acid, donating a proton to the ammonia. So that's why you get the ammonium ion right here, NH4 plus. That should be very familiar to you as well because you did that in Vesper, right? That was the ion that had that's the ion that was tetrahedral, right? And then, but it was tetrahedral. But then, like if you did the electron part, it was sorry, the electron part was tetrahedral. But then when you did the molecular geometry part, it was uh, 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 no, it was uh, trigonal bipyramidal. Oh, trigonal pyramidal, right? So you're very familiar with this already, okay? And so now you have ammonia here, right? And it's got an extra proton, so it makes it ammonium, and then the water now is a hydroxide, right? The water now is hydroxide. So in this case, water acted like a base, no, an acid there. See, water acted like an acid there, right? But in this other side, water acted like a base, right? Water can act as both. It's crazy. It's absolutely nuts. So this is your next question. Which of the following makes water different, quote unquote? Do 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 do. Water is different. Water reminds me of myself because I'm different. As Steve Jobs always says, think different. All right. So many of you have already signed in and answered. Well, most of you have already probably signed in. I mean, I meant to say answered, right? 10 people have logged in, and I'm happy to say that the 10 people that have answered their question got this one right. No trickery in this one. No trickery at all, because all those things make water different, right? All those things make water different. Water can act as both a Bronsted-Lowry acid and a Bronsted-Lowry base. And then it is also amphoteric. It's called amphoteric because of the fact it can act as both, right? And so this is what makes water different, okay? All right. So this part is super important, okay? This part is super important because it's going to dictate what you do with calculations for this chapter, okay? So the thing I want you to see here is that we have, does anybody know the name of this acid right here? Right here, HNO2. Wow. Wow. At least there was a hydro in there, and at least there was a nitrogen somewhere in there too. This is actually nitrous oxide, right? This is, sorry, nitrous acid. Nitrous acid. This is called nitrous acid, right? It's the weaker form of nitric acid, right? And so remember, this itself is the acid, yes, and it's being dissolved in water, right? But the acidic effects don't happen until you get the hydronium ion. So when you dissolve it in water, nitrous acid here, we remove the pH and remove the H, and we get the nitrite ion, and that's known as the conjugate base. Okay? And then the base here is water, right? And when water gets a proton donated to it, it becomes a conjugate acid. I cannot tell you how important it is for you to be able to tell the difference between the acid, the base, the conjugate acid, and the conjugate base. Okay? You have to know that difference. It is so important. Okay? The thing that can help you with this is the fact that generally, when it's on this side, right, on the left side, it's uncharged. And if it's uncharged, you have the acid and you have the base. But if it's on the right-hand side, right, it's going to be charged, number one. But the conjugate base will always be the negative one because it lost the proton, right? And then the conjugate acid will always be the positive one because it just gained a proton, okay? But it's important that you know the difference because there'll be many, many, many questions that will just say, right, identify the concentration of the conjugate acid. But there's four things to pick here. Which one do you find the concentration of, right? Unless you know what the conjugate acid is, right? The other easy way to remember this stuff too is the fact that the conjugate acid has the extra proton, right? So it has a proton to donate if you go backwards, right? If you go backwards, it's got a proton to donate, so it can act as an acid. And then the conjugate base here, it can act as a base because it can receive a proton if you go backwards, if you reverse the reaction, right? So just remember to be able to tell the difference and identify conjugate acid and conjugate base pairs. Here's a conjugate acid, and it's paired up with a conjugate base. Here's a base, and it's paired up with a conjugate acid. Okay? That's important. Very, very important. And then I'm going to talk about a couple more things, and we'll end it for today, right? Relative strengths of acids and bases. Acids that are above the line with H2O as base are strong acids. Their conjugate bases do not act as acids in water. Bases below the line with H2O, right, act as bases below the line with H2O as an acid are strong bases. Their conjugate acids don't act as acids in water. I know that's a very confusing statement, so there's a picture of it next slide to show you what I'm talking about. So here we go, okay? These substances between the lines of H2O are conjugate acids and base pairs in water, right? So if you look at this over here, right? These are all conjugate bases. I'm sorry. These are all acids, right? These are acids right here, and these are the conjugate bases. So here we have HCl, hydrochloric acid, right? And its conjugate bases over here, chloride. So it's a strong acid, HCl is, but on the other side, its conjugate base is not very basic, right? Negligible basicity, okay? The bigger brother of nitrous oxide that we talked about a second ago is nitric oxide. It's right here, also a super strong acid. But you bring it over here past the water line, right? And nitrate is not a very strong base, right? Not a very strong base. And you can think about the reason why that's true is because if it were a strong base, it would hold on to that proton stronger, right? And it wouldn't let it go. But since they're strong acids, they're letting go of those protons super easy, right? And if they're letting go of those protons super easy as strong acids, that means that their conjugate bases won't be strong bases, right? And vice versa. We'll talk about more of that later. Okay. Some weaker acids here, right? We've got phosphoric acid, hydrogen fluoride. Here's acetic acid. What's acetic acid? Anybody know what acetic acid is? No, you're using something else that I can't say because it's in the quiz. Acetic acid is vinegar. Okay? Acetic acid is vinegar. Like, the vinegar you use to pickle your, pickles. Do you people do that? I think people do that, right? People put salt and vinegar together and sugar to pickle pickles or pickle cucumbers, whatever. Anyway, that's acetic acid. It's a weak acid, and of course over here it's a slightly weaker base, right? But the thing that you'll see that is the strongest bases are going to be the ones that have almost no acidity, like hydroxide here, right? Hydroxide here. If it loses it's that proton right there, it becomes an oxygen with two minus charge, right? It's begging for some protons to balance out those two negative charges, and so that makes it a super strong base, right? So this is an important thing to remember here. This kind of thing. If you have a strong acid, you're almost not basic at all when you have its conjugate base. If you have a weak acid, your base is weak, but it's not as little as the strong acids, right? But then if you have almost no basicity at all, then you're going to be very strong. If you're not going to be, sorry, if you have no acidity at all, then you're going to be a very, very strong base, okay? And here's the water line, right? Here's the water line, okay? So everything that's above the water line, right here, right? Everything that's above the water line is going to have either weak base as its conjugate base or negligible base, right? If you're above the H3O line, right, the hydronium ion line, you're definitely not going to have any basicity at all with a strong acid. But if you're below the water line, right there, then you're going to have very strong bases if you can get them, right? When you pull off that proton, okay? When you pull off that proton. So that's a little chart there to explain what I was talking about before when I was saying water line and hydronium line, right? So in every acid-base reaction, equilibrium favors the transfer of a proton from the stronger acid to the stronger base to form a weaker acid and the weaker base, right? And so here, in the one that we've been talking about, hydrogen chloride here, right, or hydrochloric acid being added to water, right, gives you the hydronium ion and chloride. Both hydronium ion and the chloride ion are weaker acid and base pairs than the hydrochloric and water are, right? Water is much stronger base than Cl, so the equilibrium lies far to the right. K here is way greater than 1, right? Way greater than 1. So here's the example with acetic acid, right? This is acetic acid or vinegar. You add it to water, right? You add it to water, and now you get hydronium, and you get the acetate ion. The acetate is a stronger base than water, so the equilibrium lies to the left this time, right? Lies to the left. So it's more likely that you keep things acetic acid than them turning into acetate, right? So that's the difference between a strong acid and a weak acid, right? A weak acid will go towards where it's all split up, hydronium and chloride, whereas a strong acid will sorry, let me say that one time. A strong acid will split up, so you have hydronium and chloride, but a weak acid like acetic acid will not split up as much, right? And so you'll get less acetate, less hydronium, and more acetic acid and more water, right? And so that's the important thing there. The last thing we're going to do today before lab is this. Which of the following is a weak acid? And then we'll end the class. You can take a little break before lab. And then just be prepared to do your quiz, your lab quiz when you get back at 1:30. Yes, lab quiz is online.
And we're staying in here
to take the lab, yes, to take the quiz. This one should be a pretty easy one too, because I just said it. So far, one person has answered and they got it right. 2 people have answered and they got it right. Uh-oh, one person answered and got it wrong. So waiting here, we have 4 answers. Which of these is a weak acid? Five answers so far. 7 answers, still waiting for 5 more people. It's half and half now. 4 wrong, 4 right. Okay. The winners are winning now. The ones that got it right are winning now. Oh, someone just answered something completely out of the blue. Ooh, another one out of the blue. Okay, so this is the distribution right here. Only 11 people have answered, but that's fine. Somehow we got all 4 answers being answered here, but at least the B's have it because the B's are correct. The only one that's a weak acid up there is acetic acid because I literally just said acetic acid is a weak acid. like right before this slide. So it's an acetic acid is a weak acid. Hydrochloric acid and sulfuric acid are both strong acids. Like we were talking about last week, water is amphoteric, right? And so what happens is that water can do this thing called autoionization, right? And autoionization means that water can, if you put two water molecules together, right, one H2O and another H2O, put them together, one of the H2Os can accept a proton, right, and the other one can give up its proton. And so you end up with the hydroxide ion, which is basic, right? And then you also end up with the hydronium ion, which is acidic, okay? So when you're looking at this particular reaction, this equilibrium reaction, right? Since water can act like a base and an acid, right? You can still go through and assign conjugate base and conjugate acid, right? So if this is the acid right here, oopsies, dang it. I always forget to make the pen work. There we go. If this is the acid right here, right, that's the guy that's going to be losing its proton, right? So its pair, its conjugate base pair, is this guy over here, right? And then the one that's receiving the proton, which is this base right here, right, that water molecule too. And so this over here is its conjugate acid. Okay, so don't forget that you need to be able to identify the difference between a conjugate acid and a conjugate base from the reactants, right? And you can do that with water, even though water has, even though water is both acid and base, right? Both acid and base. Okay, so we have this thing here that you should recognize. It's called the Kc, or the equilibrium expression, right? And so for the process of water doing its autoionization, it's going to be the concentration of hydronium times the concentration of hydroxide, right? The kind of concentration of hydronium times the concentration of hydroxide. And that was really loud in my ear just now. Just got an email. Anyway, so the special equilibrium constant is referred to as the Kw of water. And so whenever you have this right here, the autoionization of water, hydronium times hydroxide, it doesn't, you can call it the Kc, which is the equilibrium constant generally, but since it's water and water is so special, we call it the ion product constant for water, which is Kw. So the Kw, right? The Kw at 25 degrees Celsius is 1.0 times 10 to the negative 14. And you're going to start seeing how useful that is in just a second, okay? So before we jump into the numbers so deeply, let's make sure that we understand what's happening here, right? In aqueous solutions, they can be acidic, basic, or neutral, right? And in a neutral solution, you're going to have the same number of protons or hydronium ions, right? Just be aware that I can go back and forth, right? If I say protons right here, this can also be what else? It can also be the hydronium ion as well, right? I use those two synonymously, right? I can interchange those two. They mean the same thing to me, okay? Anyway, so if a solution is neutral, right, the hydronium ion is equal to the hydroxide concentration, okay? And then if a solution is acidic, then the hydronium ion concentration is actually higher than hydroxide ion concentration, which makes sense, right? Because the more protons or the more hydronium ions you have, the more acidic you are, right? And then on the other side of the pH spectrum, which we'll talk about in a second, right? If a solution is basic, we actually have more hydroxide ions than hydronium ions or protons, okay? So big thing here, just remember I'll use hydronium ion and proton interchangeably, okay, when I say that, so don't get confused. Okay, so here we have hydrochloric acid, right? Hydrochloric acid, which is a very strong acid, meaning it pretty much 100% ionizes, right? And so the concentration of hydronium or protons is going to be way greater than the hydroxide. In a neutral solution of water, it's going to be pretty much equal, right? But that's even more complicated than you think. You don't have to worry about that now. But for the purposes of this, right, it's going to be equal. And then for a basic solution, hydroxide will be bigger than, will be more concentrated than uh, hydronium or proton. But the thing I want you to really notice about this whole thing is that no matter how acidic or how basic or how neutral it is, right, you always end up with 1 times 10 to the negative 14, right? You always end up with 1 times 10 to the negative 14, okay, when you're talking about the KW, okay? Doesn't matter what you have, you're always going to end up with 1 times 10 to the negative 14. So your first question is this: which of the following is true about a neutral solution? Is the hydronium or the proton concentration equal to the hydroxide? Is the is the hydronium or proton concentration greater than the hydroxide, or is it less than the hydroxide, or is it none of the above? Are you guys glad that we're like in the last leg of the semester? Like school, almost time for Christmas break. I didn't even know that school. We don't even come back to school till like January 24th. I mean, I'm gonna have like up 2 months off after we get it done. Yeah, I still get paid too, so it's great. Yeah, the first I checked because I teach forensic science in the spring, and that class doesn't start till to January 24th. So it's crazy though. I didn't know we started school so late. Crazy, crazy, crazy. Does anybody know what the last day of school was? So the week of the 14th would be the week of finals? Huh? So I'll have the 2 weeks, so it won't be a full 2 months off. Hell if I know. What's up? You can drop a lab, but you're still responsible for the report that comes from it. From your partner or somebody in the class? Why are you missing a lab? On Wednesday? Really? This week or next week? Next week. What? Well, worry about that next week then. It is important, but
if I could do it, I'll do it. I'd rather drop a lab that, I get a bad grade on.
I mean, there's really no way for you to, because we only have one section of the lab, so it has to be done that day. So, yeah. When is the game? Is it? Are you going to be like gone all day, or is it?
November 3rd. I was like October 3rd.
Are you going to be gone all day?
Like warm-ups and shoot around and stuff is around like 12-ish.
12-ish. Oh.
And then it goes on the rest of the day.
I mean, honestly, your lab grades are all pretty much good. I mean, really, the thing that you need to worry about mostly is the reports, right? Because your lab grade itself is not the report grade. It's you turning in the data, you doing your your pre-lab, you doing your, that kind of stuff. So, I mean, you can drop that easily, and the other ones are still. Have you been turning in all your labs?
Yeah.
So what's the problem? I mean, the reason why I asked.
I guess always got one grade. Always got one grade. I don't want it to be that one.
I mean, I honestly would just drop that lab. I wouldn't worry about doing a makeup because you can get the data from somebody else. And I mean, unless you don't turn in any work at all for the actual pre-lab or the data part, right? I mean, you should have near perfect lab scores. I don't know for a fact that you do, but I don't know how you can, So Sorry, it's not letting me log into the computer for some reason. And then Mary here is distracting me with her craziness. When, that's not new though. I should already be used to that. I forgot to show you the results. Okay, so the vast majority of you got that correct. The answer is quite literally A, because A is equal to equal. A is equal, right? Hydroxide and hydronium ions should be the same in a neutral solution. So, what does it mean then? What does all this mean? What is pH, right? Well, pH is a method of reporting the hydrogen ion concentration or the hydronium ion concentration. Just remember again, I might put in there H3O plus instead of just hydrogen plus, right? So make sure you know the difference, or not the difference, but know that they're the same. And so when you do pH, right, pH literally means the negative log of the hydronium ion concentration, okay? Everybody should already know, though, that the neutral pH is 7, and acidic pH is below 7, and then the basic pH is above 7, right? And so on this little chart here, which I should have made a lot larger, I apologize for that, but the highest pH you can get, right, is 14, and the lowest pH you can get is 0. Why is that, right? Why is the pH scale 0 to 14? Well, remember, right, no matter what you do, no matter what acid or base you have, right, and whatever concentrations you have it, it's always going to end up the hydronium ion concentration times the concentration of the hydroxide always equals 1 to the negative 14. And why does it always do that? It's because Kw is 1 times 10 to the negative 14, right? And that's the reason why the pH scale is 0 to 14. Does that make sense? Right? So mathematically, it bornes out that the pH scale can go no higher than 14. Interestingly enough, though, you can get some acids that are super, super strong, and it can go way past 0, like go into the negatives, right? But you can't get bigger than 14. So, catching back up again, right? Only the digits after the decimal point are significant figures and logarithms. And so if I were to give you a hydronium ion concentration, all you need to do is do the negative log of that hydronium ion concentration. Was she in there? And so if I give you the hydronium ion concentration, all you have to do is take the negative log of the hydronium ion concentration, and you'll get the pH, right? And it'll fit on the pH scale. And so notice here, right, as you have a pH, which is the negative log of the hydronium ion concentration, you can also have a pOH, right? Which is the negative log of the hydroxide ion concentration, right? So you have a pH and you have a pOH. You add those two together, it should equal 14, right? Because you can go no higher than 14 on the pH scale, right? So this is just some examples of stuff. Human blood is neutral. Seawater is slightly acidic. Slightly basic. Other household ammonia, household bleach, all that stuff is basic too. And then on the other side of the spectrum, right, you have stomach acid, which is super acidic because stomach acid actually is hydrochloric acid, so that's a pretty strong acid. Does anybody know why hydrochloric acid doesn't burn a hole straight through your stomach? Yeah, so there's a mucus lining on the inside of your stomach that keeps you from getting burned. But so when you throw up after being drunk after a night, right? Your throat like burns, and the reason why your throat burns after you throw up is because that mucus lining is not in your throat, right? But it is in your stomach. What was I thinking? Oh yeah, so there's other pH scales too, like I was talking about before. If you have pH, that's the negative log of the hydrogen ions or hydronium, but you can also have pOH, right? Like I was saying before. And so if you have pOH, right, then that's negative log of the hydroxide ion concentration. So you can use either one to figure out what the concentration is of hydroxide or pH to figure out the concentration of hydronium ions, right? And then you also have the pKw, right? And in the pKw, right, that's just doing the negative log of the 1 times 10 to the negative 14. And that actually gives you 14, I think. So, that's the kind of thing you can do with that. So here's some examples, right? Oh, I was right, man. I'm so good at this. Anyway, so remember, right? Just a reminder here, right? you can do the concentration of hydronium times the concentration of hydroxide, and that should give you Kw. And Kw is 1 times 10 to the 14. And again, the 14 is indicative of the reason why we have 14 as being the highest number on the pH scale, right? So what you can do then is you can take the negative log of the hydronium ion concentration plus the negative log of the hydroxide ion concentration, and that should give you the negative log of the Kw, which is 14, right? And so that's how you can get down here to this point here where it's pH plus POH equals the pKw, which is equal to 14, right? So you'll get problems from me, you'll get questions from me in the assignments and in the quizzes and in the exam that tell you, I'll give you this concentration of something, and you'll have to use you have to use these relationships right here to figure out, what the pH is, what the POH is, what the concentration of hydronium is, or the concentration of hydroxide is, okay? So your next question is this. What does the P in pH tell us? What does the P in pH tell us? Acid-base chemistry is actually one of my favorite chemistries. I feel like I say that about everything. Because I just told you my favorite chemistry was kinetics, didn't I? Oh, that's funny. That's so funny. My mood is so changeable. All right. Let's see here. P. I've got 4 responses so far. I got 4 responses so far. Waiting for a couple more. That should be everybody. All right, so the vast majority of you got that question correct, right? The answer is, in fact, B, right? The answer is, in fact, B. And the reason why it is B is because, like I said in the previous slide here, right? Negative log right here, right? Not negative log, P here, right? pH here is the same thing as the negative log of something, right? And so in this question, what does the P and pH tell us? It's the negative log of a quantity. So don't confuse that with ln, which is the natural log, right? There's the natural log and then there's the negative log. Those are 2 different things. Don't get that confused, right? And then you have e raised to the quantity. If you remember what e is just a number, a constant number like 2.7153555389 or something like that. But the only part you need to remember is the 2.71 part. But that has nothing to do with this, right? That has nothing to do with this. And then 10 raised to a quantity is something else we'll do in a second. Okay, so how do we actually measure pH? Right? How do we actually measure pH? One way to measure is using a pH meter. Okay, pH meters are used for the accurate measurement of pH. Electrodes indicating small charges in voltage can detect pH. And so this is a very simple, very old school pH meter, right? No, not old school, but like it looks old to me. And you can stick it in there, and you can see that we got white vinegar here, and white vinegar here has a pH of 2.45, right? A pH of 2.45. And so when you have that pH, quite literally, if you have quite a meter, right, and you stick it in if you have that meter and you have just some unknown solution, you don't even know what the solution is, and you have that pH meter and you stick in the pH meter into the solution, it gives you pH. What can you find out from that? You can find out the hydroxide ion concentration, you can get the hydronium ion concentration, you can get the POH, right? You can get all kinds of stuff, okay? And the one thing you can do is that if you stick it in there and it reads 7, you know it's safe to touch because it's neutral, right? But if it's going to read 2.45, maybe you shouldn't touch it because it's a little bit acidic. Well, vinegar is not that dangerous. But, take it down to 1 or less than 1, then maybe you shouldn't touch it. Have you ever used bleach and you got some of it on your hands and you can feel it getting really slippery in your thumb and your finger when you do this? It gets super slippery. That's because that bleach is actually breaking down the cell membranes of your skin cells, right? You leave it there long enough, you won't have anything on your epidermis left, right? And so that's what bleach does. Okay, it oxidizes your bleach is actually a molecule called sodium hypochlorite, and sodium hypochlorite is a super strong oxidizer. That's why it kills germs so easily, right? And so not only can it break open the cells of germs, it can also break open the cells of your skin cells, right? And it's literally killing your skin cells when you feel that soapiness, right? You feel that soapiness, that slipperiness, right? And that's why you got to be super careful about that, right? Back to the topic at hand, right? You can use a pH meter to figure out what the you can use a pH meter to figure out what the pH is of a solution, and I might give you a problem on an exam or a assignment or something that says, "Hey, I have an unknown solution of this pH, right? Figure out all this stuff for me." Right? That's the kind of question I might ask you. Okay? So, how do we measure pH? Well, another method is with indicators, right? So, I don't know if you guys ever did this in elementary school or in high school. People can use what is it called? Cabbage water, red cabbage water, right? You can boil cabbage water, and and it will be this like really dark purple color. But you put it into certain acidities or certain basicities, and it will change the color, right? Huh? Because red cabbage is purple.
Oh, I was confused because you said red cabbage.
Well, I think they call it red cabbage, but it's actually purple colored.
I don't eat cabbage. I love
That's a weird question to ask. I guess it makes sense. It makes sense. So another one you'll use is called phenolphthalein, phenolphthalein, which is this right here, right? And notice the pH at 10 is super pink, but when you get to like acidic, it's colorless. And the reason why I bring this up is because next week in lab, you'll be doing a titration experiment where you use phenolphthalein, okay? And that's the colors you'll have. Okay, depending on how basic something is, or how basic something is, how basic something is, or how acidic something is, right? So this is just a list of different indicators you can use, right? For methyl violet, right? If you're at the basic level, it's yellow to violet, right? Whereas over here you have alizarin yellow, and it's like red. It's red to yellow. So you can use all kinds of different. I don't want to go through all those different indicators, but the one that you will use for sure is phenolphthalein, and phenolphthalein will be pink to clear, right? Pink to clear. So let's discuss strong acids, right? You will recall that the 7 strong acids are, oh my God, see, this is a you're welcome moment. These are the 7 strong acids right here. So if I ever ask you a question like, which of the following is a strong acid, right, you should know which one it is, or which of the following is not a strong acid, right? So we have strong acids here: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, uh, sulfuric acid, chloric acid, and perchloric acid. Those are all very strong acids. Okay, these are by definition strong electrolytes and exist totally as ions in aqueous solution. So what happens here is when you have this strong acid HA, you add it to water, right? And what do you get? You get completely hydronium ion concentration and hydronium ions and the conjugate base, right? So for a strong monoprotic acid, the hydrogen ion concentration will equal the same concentration as the acid itself, right? So you have 12 molar hydrochloric acid, right? That will also be the concentration of the hydronium ion concentration. Does that make sense? It will always be the same because they dissociate completely. Strong acids do, right? If I have nitric acid and the nitric acid is 2 molar, right? Nitric acid, then the hydronium ion concentration will also be 2 molar. Okay. Contrast this though with weak acids in a second, right? Because we got to talk about strong bases first, right? Strong bases are soluble hydroxides, right? Which are alkali metal. Strong bases are soluble hydroxides, which are alkali metals and heavy alkaline earth metal hydroxides. So things like calcium, strontium, and barium, but their solubilities are low. But again, these substances dissociate completely. For example, when we have here some metal, say sodium with hydroxide, you get the metal ion there, and you also get the hydroxide ion, right? So when you have a strong base, it's the same thing as it is with a strong acid. The concentration of strong base, so you say you have 2 molar sodium hydroxide, the hydroxide concentration will also be 2 molar, right? For strong bases, okay? Let's see here. Strong bases are soluble hydroxides. Yes, yes. Let me make sure I got this all written down or told you. Yeah. So this is your next question. Which of the following is not true about strong bases? Strong bases are soluble hydroxides. They dissociate completely in aqueous solution. They consist of a transition metal, or all the above is true about strong bases. And I'll tell you now, we're not going to do a lot with strong bases in like the actual gist of this lecture, but you still need to know what they are. We're really going to focus on weak acids and weak bases, because those are the ones that actually go to an equilibrium concentration that is different from the acids concentration. Huh? Did you say you'd be the perfect? Did you say you'd be the perfect murderer?
We were talking about like.
You know this is being recorded, right? You know this is being recorded.
So if you do a murder, you need to do it like Canada or something. No, because our teacher, he was like, you know, like those weird golf teachers that always talk about like weird stuff. So we were talking about death sentences, and it was Halloween time.
Okay. Check this out. I'm very proud of most of you here, because the answer to this question was actually C, and half of you got C, right? It was a little tricky here, okay? Because I told you in the previous slide that strong bases are usually of the alkali metals or heavier alkali earth metals, right? And so C is the one that's not true because it doesn't really consist of the transition metals, right? So good job on you if you picked C there. You're paying attention. Or at least you remembered what I said. So good job on that there. I'm going to move on from the conversation that one of my students is going to be a good murderer, and we'll just keep on going on that. We'll just forget that happened, okay? All right, so this is what we'll focus on here in class mostly, right? And it's the dissociation of a weak acid, right? Where we have an acid, say acetic acid, plus water, right? Will get you the hydronium ion, right? And its conjugate base. And notice that it's a reversible reaction because all equilibrium reactions have arrows going forwards and backwards, right? Notice compared to this, right, where the arrow is only going one direction. When the arrow goes only one direction, it goes completely to dissociation, right? It doesn't go back to being what it was before, right? Same thing here, right? Strong acid to water, it has only one arrow, right? But when you do a weak acid to water, you actually get a reversible reaction. And the reason why is because not all of the acid will actually dissociate in the water. And so you get some original acid left over, and you get some of the acid dissociated, right? So that equilibrium is known as the acid dissociation constant, okay? Also known as Ka, right? And it's the same as every other reaction we've done in this class. When it comes to equilibrium expressions, we always have the products over what? Reactants, exactly, right? We always have the products over the reactants. So here, the products are the H3O and the A minus, right? And then the reactant here is the original acid, okay? So the larger value of Ka, the stronger the acid, right? So the larger the value of Ka, the stronger the acid. So you'll see that most of these will have lower Kas because of weak acids not being able to dissociate as well. So here's a list of weak acids, right? Here's chlorous acid, hydrofluoric acid, nitrous acid, benzoic acid. The one we'll talk about the most here is acetic acid. Phenol is also weak acid too. Hydrocyanic acid, hypochlorous acid. Those are all weak. And notice, right, that their Kas are all super close to zero, right? -2, -4, -4, -5, -5, -8, -10, -10, right? So they have very small Kas. So if you see an acid, right, and it has a Ka that's super close to zero, right? Like with these exponents, these negative exponents on the scientific notation right here, right? Know that it is a weak acid. I might ask you a question. This unknown acid has a Ka of 1.8 times 10 to the -8, right? Is it a weak acid or a strong acid? It's a weak acid. Okay. Make sure you know that difference. Okay. So when you're looking at then the comparison between a strong acid and a weak acid, right? What is present in the solution for a strong acid versus a weak acid? Well, strong acids, like I said just a second ago, will completely dissociate into ions, whereas weak acids only partially dissociate. So here we have a strong acid, right? Here we have a strong acid, and here you can see that there's half the amount of the particles here are H3O, and the other half is conjugate base, right? By the way, if you're not familiar or if you don't remember, right, um, in the general sense, whenever I say A minus like that, right, that's a conjugate base, right? That's a conjugate base. And then H3O is the conjugate acid, right? And conjugate bases always have a negative sign, by the way. And you see here that in a strong acid, there's 1, 2, 3, 4, 5, 6, right, of the conjugate base. And then 1, 2, 3, 4, 5, 6 of the conjugate acid, which is the hydronium. So every single ion of this acid broke apart into its conjugate base and made H3O. But when you come over here to weak acid, right, it only partially dissociates, right? Here's one H3O molecule, right? Only one, but the rest of them have stayed, right, together. See? The rest of them have stayed together, right? Not as many H3O, almost no H3O molecules at all. Most of them stayed the original acid, for example, acetic acid. So the point of this is that acetic acid being the weak acid, right, will stay together most of the time, right, leaving you with mostly water and acetic acid. Whereas hydrochloric acid will break into, because it's a strong acid, break into hydrogen ions and chloride ions completely, right? And so when we do equilibrium equations, or we work on equilibrium, when we work on equilibrium expressions, it will almost always be with a weak acid. Okay, almost always be with a weak acid. Okay. So next question: in the equation for the dissociation of a weak acid, what is A minus? So far, everybody's got it right. Oh, dang, someone got it wrong. I'm gonna have to see who this person was. I'm gonna have to see who this person was. It was probably the same person that got it wrong last time. Got 5 more. 5 more. 5 more. I'm still waiting for 5 responses. I literally just said this on the previous slide. Still waiting for 4 people.
I have a question.
Sure.
Did you explain why a strong acid completely dissociates
Not specifically, no.
versus okay.
Honestly, because you don't really need to know that, right? Because I'm not going to ask you about it. But if you want to know, I'll tell you, right? So if you think about it, right, water, right, is polar, right? It's got the positive side with the water, the H's, and the negative side with the oxygen. And then so when you have something like hydrochloric acid in there, one side's super negative and the other side's super positive. So the water can go around and solubilize it, right, and make it completely dissolve, right, just like it does with salt, right? But then you have something like acetic acid, right, that has a whole bunch of carbons. And so it makes it a lot less polar, right? And since it's a lot less polar, it'd rather stay together than break apart with water. Does that make sense? Yeah, it's absolutely about, It's absolutely about what we call the intermolecular forces, right? Like polarity, dipole moments, ion dipole moments. So it's a good question to ask, absolutely. And you'll dive deep in that later, but not right now. Okay, so the answer is for this one. Absolutely, the answer is in fact D, right? Because it is a conjugate base. A minus is a conjugate base, right? So good on y'all for getting that one right. Good on y'all for getting that one right. So given all this information, right? Let's see how we do this. How do we calculate a Ka from a pH? Given that I have a pH of, the pH of a 0.1 molar solution of formic acid, right? So notice how there's a carbon there, some oxygens, and a carboxylate there, right? So this is going to be a weak acid because there's carbon in there. But anyway, at 25 degrees, is first thing I want to tell you is because I feel like a lot of times we're having issues pulling out the correct information to do a problem, right? Um, if there's nothing else but the 25 degrees here, right? You don't need the 25 degrees for anything, okay? Don't dwell on that, okay? Do not dwell on that, okay? Because in my expression here, is there a big T in there anywhere? No, so you don't need the 25 degrees. We're giving you the extra information to confuse you, but don't be confused by that stupid trick, okay? So I have formic acid, right? I need to find a Ka, and its pH is going to be at 2.38, right? And so how do I do that? How do I figure that out? Well, the first thing I can do here is figure out the fact that we have here the formula, right, for the formula for formic acid, okay? And the thing that you've got to figure out is, and it already tells you there anyway, but I would, if I were you, write it out so that you know what it looks like. Be like HCOOH, right, plus water gives you H3O plus, right, plus HCOO minus. Okay, I'll write it out like that, just so you know what the actual equation is. The good thing about writing it out too is you can figure out whether you need to have any kind of coefficients and stuff like that too, making sure everything is balanced. But usually though, with these monoprotic acids, monoprotic means one proton acids, right? It's always 1-to-1 ratio. Okay, so this part right here will be at the top of the expression, the H3O and the HCOO minus, right? The formate ion. And then on the bottom will be the acid and the water, but the water, you don't have to worry about the water, right? It's just going to be the acid. Sorry about that. Okay? And so now that you have that, you can fill out the Ka expression, H3O plus times the concentration of HCOO minus divided by the unionized acid, which is the formic acid, right? So to calculate the equilibrium, to calculate the Ka, we need the equilibrium concentrations for all three things. Okay? We need the concentration for all three things. So here we go. We can find the H3O concentration because it's the same as the HCO minus concentration from the pH. Okay? So when you have the H3O concentration, that's going to equal the HCO minus concentration, right? And you were given in the previous problem here, you were given the previous, not in the previous problem, but in the problem itself, that the pH was that, right? 2.38, right? And so you know that pH equals the negative log of the hydronium ion concentration, right? So we take it over here, right? To undo a negative log, what do? You do 10 to that number, right? You do 10 to that number, which, by the way, if you have your calculators here, I'll show you how to do that, right? Because you're going to need it later. Does anybody have their TI-30 with them?
No, I got this.
No, not that one.
I got this right
Yeah,
here.
that works too.
No, it goes to the side. It does all the other.
No, you're only supposed to be using a TI-30 on the test, though. I want to show it on TI-30 calculator first, because most people have a TI-30 calculator. Anybody have a TI-30? Thank you very much. There we go. Okay, so I should have brought mine. Oh well. I need to stop asking students to provide me
It's in your calculator.
with the tools I need to teach. Here we go. So on this calculator right here, right, there's a button right here just above, ooh, that was bright. There's a button right here just above the log button that says 10 to the x, right? That's the button you should be using, okay? That's the button you should be using, 10 to the x. And so it's 10 to the x, and what is the x? It's that negative pH right there, right? So to undo a log on this side, to undo a negative log on this side, right, of the equation, you've got to do 10 to the negative pH. Make sense? And then vice versa, right? To undo a 10 to the negative pH, what do? You take the negative log, right? One undoes the other. Thank you very much. So don't forget the 10 to the x button on your calculator. And when you do that, you do 10 to the negative pH, and you get 4.2 times 10 to the negative 3. And that's the concentration of the both the H3O and the HCOO minus. Okay? So then we take it to our ice table. Oh, you thought we were done with ice tables, didn't you? Because you thought, oh, in solution equilibrium we did ice tables, but we're done with them now, right? No, we're not done. So now we can set up our ice table, right, where we know that the initial concentration, right, of the formic acid is 0.1 molar, and then we also know that the ion concentrations in the beginning is 0 molar, right? And then we find the equilibrium concentrations by plugging in that number that we found, right? That number that we found just in the previous slide, so that we can figure out what the equilibrium concentration is, okay? So notice here, I mean, there's the equation that I wrote out for you just a second ago, right? Formic acid becomes hydronium ion or protons plus the formate ion, right? So in the table, we start out with the initial being 0.1 because that was given in the problem, right? And of course, this is initial, so there should be 0 H3O plus and 0 formate ion, right? But then we found out in the previous slide when we did the 10 to the negative pH right here to figure out what the concentrations were, right? That the concentration change, right, is 4.2 times 10 to the negative 3 molar, right? So that what that means then is that as we reach equilibrium, right, this initial concentration of formic acid will be subtracted by the 4.2 times 10 to the negative 3, right? Because that's how much of the initial concentration of formic acid we're losing. So if we're losing that much on that side, the reactants, where is it going to go? Exactly, it's going to go on the product side. So that's why on the product side, you have plus 4.2 times 10 to the negative 3 and plus 4.2 times 10 to the negative 3, right? So all you have to do now is figure out this math down here for the equilibrium concentrations, right? We don't have to do anything with that at all because it's just plus that, and you'll get these, right? Because they were 0 before. But over here, you do have to do the subtraction of 0.1 minus 4.2 times 10 to the negative 3 and get you that number right there. And that will give you the equilibrium concentrations, okay? Once you get those equilibrium concentrations, all you have to do is put it all together in the Ka expression, right? 4.2 times 10 to the negative 3 times 4.2 times 10 to the negative 3. This was the hydronium ion concentration. This was the formate ion, right? And this is the formate, right? And then this was the, down here, the original concentration of the acid, which was the formic acid concentration, right? So you plug them all in to the Ka expression, and you get 1.8 times 10 to the negative 4. And that's the Ka of formic acid. It's good stuff, good stuff. So the next thing you can do is you can calculate the percent ionization, right? Where you take the concentration of H2O at equilibrium divided by the initial concentration, which was the 0.1, and multiply it by 100. So in this example here, our concentration of H3O, remember we calculated it to be using the 10 to the negative pH equation, calculated it to be 4.2 times 10 to the negative 3, right? And then the problem gave us that it was a 0.1 molar solution of formic acid. So you just plug it in there, right? Products over reactants again, right? And times 100, and then you get a percent ionization of 4%, right? So it's super easy to figure out the Ka of the equation of the acid-base problem, and figure out the percent ionization just by knowing what? The pH, right? And the original concentration. So, real quick here, next question. In the example with the dissociation of formic acid, the H2O concentration is equal to what? All right, let's see how people are answering this question. Oh, so far everybody's got it right. But there's only 4 people, so 5 people now. Woohoo! Still need 2 more people to answer. One more person to answer. Who is it? Oh, okay. There it is. There it is. All right. So again, a couple of people got this one wrong, but that's okay. All right. The answer is in fact C. Right. The answer is in fact C. It's definitely not B, because remember the Ka. Right. The Ka equals the product over reactants. Right. So it can't be that. But it does equal, the hydronium ion concentration does equal the conjugate base concentration. Okay, in this case, the conjugate base was the formate ion, right? So this is the last thing we'll talk about today, because you'll need it for discussion section today. Okay, the method to follow in calculating pH using the Ka, right? The first step you gotta do is write the equation for the ionization equilibrium, which I showed you how to do that a second ago. The second to do is write the equilibrium constant expression, right? Which is the products of the reactants thing. Ka equals the products of the reactants, or you could say Ka equals the conjugate base times the conjugate acid divided by the original acid, right? And then set up your ice table, right? And then do the substitution and solve for x, right? That's how you're going to do this, okay? So here's the example, okay? I have now acetic acid here, right? I want you to calculate the pH from a 0.3 molar solution of acetic acid, right? And it says at 25 degrees. Do you need that number? No, you do not need 25 degrees. So don't freak out when you have a leftover number. So the equation is then this: acetic acid plus water makes the hydronium ion and what? The acetate ion, right? And so the Ka expression will be Ka equals the hydronium times the acetate divided by what? The original concentration, okay, of the acid, which in this case was 0.3 molar, right? So you've got that equation now. You've got to set up this ice table, right? Remember, acetic acid here becomes hydronium ion plus acetate, and our initial concentration of the acetic acid was what? 0.3, and our initial for hydronium and acetate is what? 0, right? Does that make sense so far? Okay. So what is the change in concentration going to be? Well, the change in concentration will be, of course, we're going to be losing X, because we've got to solve for X. We're going to be losing X from the original concentration of acetic acid, but we'll be gaining X, right, plus X and plus X for both the hydronium and the acetate because they're going to be the same concentration, right? Because it's a 1-to-1 molar ratio between the hydronium ions and the acetate ions. And so, in the end, then, we have our equilibrium concentrations being 0.3 minus X for the acetic acid, and then just X and X for both the hydronium ion and the hydroxide ion. Okay, that's helpful because now we can set this up, right? We can set this up where we can plug in our variables. We know that hydronium ion concentration from the table was X. We know that acetate was X from the ice table. And then we know that the acetic acid was 0.3 minus X, right? So this is the part where you say thank you to me because we know for a fact that when it is a weak acid, right, the number is like 5.0 times 10 to the negative 5, right? It's a really small number, right? So if you assume that X is so much smaller than 0.3, right, then all you have to do is just drop the X, right? You can just drop that X because you know that for a weak acid, the number is so small. This association is so small. It's like to the negative 5 or negative 4, negative 6 or whatever it is, right? So it's almost zero anyway. And so if you drop that and just make that zero, all you have left at the bottom then is what? Just 0.3. Why does that make that easier for you to solve this expression? Why are you thanking me for this?
Because you say we don't have to use a quadratic formula.
Exactly right. Now you don't have to do the quadratic equation anymore, right? Because you no longer have a 2x term, right? Or a bx term for the quadratic. Does that make sense? You look confused. You remember from the last one we did, I made you do the quadratic equation to figure it out? Because you had like ax squared plus bx plus c, right? When you figured out what the expression is, right? The reason why that was is because you had to figure out what this x was right here after you FOILed it, right? But now I'm telling you, for weak acids, just for weak acids, right? You can assume that that x is 0. So that just drops one of those terms, right? And so now the equation you get then is just going to be the Ka, right, equals the Ka equals 1.8 times 10 to the 5th, right? And then all you have now then is this here, x squared from that up there divided by 0.3. Instead of saying x squared divided 0.3 minus x. Does that make sense? Having that minus x there makes you have to do the quadratic equation. Does that make sense? But since you don't have to do it anymore, because I'm telling you it's 0, right? It makes it a lot easier, right? All you have to do is now solve for x squared, right? By the way, this Ka right here is a number that everybody knows. It's from that table that I showed you before. Oop, went too far, right? Here's acetic acid, right? Right there. So you can find it on a table. Okay. And so you know that the Ka is the acetic acid Ka equals x squared divided by 0.3. So you solve for x and you get 2.3 times 10 to the negative 3. Right? Does that make sense? Everybody got that? So if x equals that, right, all you have to do is take the concentration of this, right, by doing the negative log, because this is a concentration. And if you do the negative log of the hydronium ion concentration, what do you get? You get the pH. Does that make sense? I'm seeing lost faces out there.
Why look at me?
I'm looking at everybody. You just happen to be looking at me when I was looking at you, but I'm looking at everybody. Does that make sense? Okay. Does everybody know how to solve for x here? You have 1.8 times 10 to the negative 5 equals x squared over 30. You just get the numbers on one side, and then you'll have left over just x squared, and then you take the square root of both. Right? And that's how you get the 2.3 times 10 to the negative 3, right? And the thing about it, though, is that just gives you the hydronium ion concentration. The problem asks you for the pH. How do you get the pH from the hydronium ion concentration? You take the negative log of the pH. Negative log of the hydronium ion concentration, and you get the pH. Make sense? I could just make it hard on you and say, no, that's not zero. Actually put in there, leave that there. But then you have to use the quadratic equation. But I'm a nice guy. Well, you didn't seem very happy about it a second ago. No one even said thank you.
Because we're
Also, get your stuff watched.
I'm just saying, like, no one even would realize that I helped you out there, except for one person that said you don't have to use the quadratic equation anymore. Like, come on, guys. If you're not excited about it, I won't make it easy for you. All right, so when evaluating a Ka expression of a weak acid, which term is so small that we can assume that it's zero? Which term is so small that we can assume that it is zero? Yes, that is correct. This is the last thing we're doing. You just really need to go through that to be able to work the problems in discussion. I was really hoping that I get more of a gratitude from that, but I
promise you, when you start, when you have to start doing stuff, I'll be like, okay, well, thank you for that.
Whenever I'm watching this video, I'll be like, oh, wow.
That's why you did it. It's gonna click eventually.
okay. Okay, I'll give you that. I'll let you. Okay.
You know it's gonna click eventually.
It will.
But until then,
All right. So the vast majority of you got that one correct. Again, I'll have to see who that was there that got. Two people got this one wrong. Oh my God. Holy crap. Okay. For those two who got this one wrong, make sure you remember, okay, that it's x minus right here that you can assume is zero. Because right here, right, this x minus right here is the one that's so small, we can assume it's zero because it's what? A weak acid, right? So it's going to have a number that's going to be times 10 to the negative 5 or times 10 to the negative 4. So that's why you can assume that's zero. Don't assume anything else is zero. Just assume that that is zero, okay, on a weak acid. I'm going to go look in here and see who answered this incorrectly. Give him a good talking to about that. That being said, before you go to the discussion, though, this only works in a weak acid, okay? If you're doing a regular, just a run-of-the-mill chemical equilibrium problem like we did last time, you have to use the quadratic equation, okay? But if it's a weak acid, you can assume that the minus x is zero. The first thing it says is to draw the correct Lewis structure for phosphorus acid, right, H3PO3, below, identify its steric number, electron geometry, molecular geometry, the hybridization of the central atom, and its polarity. And the reason why I had all that there is, of course, because I'm going to continue testing you on Lewis structures and geometries and stuff like that. But also the other reason why, too, is because when you look at this acid right here, it looks like it has 3 protons right there, but when you draw its Lewis structure, you can see that it doesn't actually have 3 protons that are available for a donation as a Bronsted-Lowry acid, right? So the first question, right, of course, is to draw the Lewis structure. So it's quite easy, actually. Always have the phosphorus in the center, right? And then the part that's easy is this part here, because this is just like phosphoric acid, right? Phosphoric acid and phosphorus acid have those two the same, right? Where it changes is the fact that phosphorus acid only has 3 protons on it, so, 3 oxygens on it, so instead of 4, so that we can complete the outer shell of phosphorus, we actually have to have 5 bonds to it, and the only way we can get 5 bonds to it is by drawing it like this, right? Drawing it like that. So that's the correct Lewis structure for phosphorus acid, okay? And that's very different because phosphoric acid, the one that's more common, which is the strong acid, actually has this proton connected to one of the oxygens right? And then the other one has a double bonded oxygen there. So that's why this one is slightly different. It's almost a trick question. I asked several people before I gave you this. Is what is the Lewis structure for phosphorus acid, and how many protons can be used as an acidic proton? And almost every single person I asked thought it was three, right? But in fact, it's only two. Okay, and the reason why it's only two is because the only protons that can be be acidic protons are the two protons that are on the oxygens, right? Uh, the reason why that is because the phosphorus. So for something to be acidic, right, the thing that the proton is attached to has to have a different electronegativity, right? It turns out that both phosphorus and the hydrogen right here, where it's connected right there, both have the same electronegativity. So that alone says it can't be an acidic proton, right? But you already know for a fact that the electronegativity between oxygen and hydrogen are very different. They're off by like one. On a scale of 1 to 3, they're off by like one entire unit. So that's that in the general chemistry sense, right? In the general chemistry sense, the protons on the oxygens have a different electronegativity, and that's why they're the ones that are acidic. But in the even more, I guess, organic chemistry sense, things that are more acidic become more acidic because of resonance stabilization. For example, if there was a base that were to come over, like a hydroxide, came over and takes that proton right there, right? That there's a bond between the proton and the oxygen, and this bond would come down, right, and form a double bond there, and then make this bond from this double bonded oxygen go there, and then you get a structure that looks like this. That looks like that, right? And now you have a negative charge right here, okay? And so on that oxygen right there. And so what we call this is called resonance stabilization, right? You can only do resonance stabilization if you have lone pairs, right? But a proton and a phosphorus doesn't have a lone pair to do that with. But oxygens have plenty of lone pairs, right? And so that's why they can do this thing called resonance stabilization. And the reason why I showed you this is because when it comes down to it, it loses one proton. You're like, so if it loses one proton, how does it become a negative charge? It becomes a negative charge because of this right here, this one single bonded three lone pair oxygen right there, right? So what I was looking for you to draw though, as the Lewis structure here, was that, right? And I was hoping that you draw it such that you had one hydrogen that was connected to the phosphorus, and then the other two were connected to oxygens. So that you could see that, in fact, based on its Lewis structure, this is a diprotic acid, not a triprotic acid like most people would think. Now, if that were phosphoric acid, that would be different, right? Because on phosphoric acid, so let's just be clear about what's happening here. So that's phosphorus acid, right? Phosphoric acid looks like this. Right? That's phosphoric acid right there. And notice that every proton on phosphoric acid is connected to an oxygen, right? And that's the reason why phosphoric acid here is triprotic, and then phosphorus acid here is diprotic.
And then anything that doesn't give like the double OH stuff is monochromatic.
Right, right.
Wait, why is it diprotic? Sorry, can you repeat that?
Phosphorus acid here is diprotic because it only has two protons that can be used as acidic protons,
Oh, okay.
right? Because these are the two protons that are attached to the oxygen right here. On the other hand, though, phosphoric acid, which is a strong acid, has all three of the protons attached to oxygens, right? So that's why all three of these can actually be used as acidic protons, okay? So it's a very, very huge, very large misconception that phosphorus acid is triprotic, because looking at it like just by its formula, doesn't it look a lot like phosphoric acid, right? I mean, everybody thinks that it's going to be triprotic because it looks a lot like phosphoric acid. But nope, in actuality, phosphorus acid is only diprotic, and you can see why it's diprotic, right? You've got to maintain 5 bonds around the phosphorus, right? But the only way to have 5 bonds after you draw a correct Lewis structure, right? After you draw the correct Lewis structure, is by having one of the protons actually attached to the phosphorus so that you can have a double bond with one of the oxygens. You don't have to do that with the phosphoric acid because you already have 3 bonds from the 3 oxygens and a double bonded oxygen right there, right? So, and you'll see if you go through, and I'm not going to make you do this, but if you want to do this, go through the 6 steps, right, of making correct Lewis structures. And once you count up all phosphorus's electrons, count up all the electrons that are available from the oxygens and the hydrogens, right, you're going to end up with a point where you have to make a double bond between something, and the only thing you can make a double bond with is an oxygen by itself, right? We won't go through that now. That was like months ago, but that's the reason why. Okay. And I'm talking to you about this now because we're about to jump into doing acid-base equilibrium with multiprotic acids or polyprotic acids, right? So I'll give you a name, right, or a formula, and you're going to have to figure out whether or not it's diprotic or triprotic, and most are pretty easy to figure out. It's just phosphorus acid is the one that's a little bit ambiguous, but it actually isn't ambiguous. It's clear when you draw out the Lewis structure that it's the way it is there. It's diprotic. Okay, so here's the answer that I was looking for right there. That was the answer for that. Okay, so looking at that next problem, right, the next question in the problem was, what is a steric number? Its steric number is 4, right? And then it's, let me get the pen working again. I wish there was an easier way to do this. All right, its steric number is 4, right? Because it has 1, 2, 3, 4 electron domains, right? And when you have a steric number of 4 with a steric number of 4 electron domains and no lone pairs, that means electron geometry and molecular geometry is going to be what? Tetrahedral. Right? Both are going to be tetrahedral. Okay? Now, if it had a lone pair, it'd be trigonal pyramidal, right? But it's not a lone pair. It's 4 bond groups with no lone pairs, so it's going to be tetrahedral. Okay? And then it's asking for the hybridization of the central atom. The central atom is phosphorus, and it has 4 electron domains on it. It's a steric number 4, so we're going to say that it is sp3 hybridized. And very lastly, what is its polarity? We can see that this side over here has a bunch of oxygens right here, or just this one big oxygen on this side, right? And on this side has a bunch of protons, so it's definitely polar. Okay, so that's everything from the first part of the question. We've already answered question A, right? We've already answered question A, and I actually want to erase something again so that I can use it as an example. I'm going to erase that. I'm going to erase that. Erase those arrows. There we go. Okay. You can tell that these acid-base equilibrium problems take a lot of paper. I mean, like space. Okay, so we already know it's diprotic for the reasons I explained a few minutes ago, right? And then, so the next question is, if you have a 25 ml sample of phosphorus acid and you titrated it with 0.102 molar sodium hydroxide, and it requires 23.3 mils of it to reach the end point, what is the concentration in molar of the phosphorus acid, right? So you should have done titration calculations back in Gen Chem 1, okay? So this is reaching back to your Gen Chem 1 days. But just in case you don't remember how to do a titration calculation, the first thing to do is to figure out how many moles there are of sodium hydroxide that actually made the phosphorus acid go to its endpoint, okay? The way you do that is you start out with the volume that you have, right, of the sodium hydroxide, and everything is always going to be in liters, so it's going to be 0.0233 liters of sodium hydroxide, right? Because remember, moles divided by liters is what molarity is. So that's why you got to make it liters, okay? And then you're going to convert that into moles by saying how many moles of the sodium hydroxide you had. Oops, didn't mean to do that. Let's go back here. There we go. And so it says right there that the concentration of the sodium hydroxide was 0.102. So that's going to be 0.102 moles of sodium hydroxide. And all that is over, how much is that over? It's going to be over 1 liter, right? Because that's what the unit is for molarity. 1 liter of NaOH, like so, okay? Which is great because now you can cancel out liters of sodium hydroxide and you're left with moles of sodium hydroxide. So how many moles of sodium hydroxide do we end up with here? It is, I believe, it's 2.38 times 10 to the negative 3 moles of NaOH. Okay? We're not done yet, though. We've got to figure out still what the concentration of the phosphorus acid is. How do we figure out the concentration of the phosphorus acid? We have to use the molar ratio, the stoichiometric ratio, right? And the reason why you needed to figure out what the balanced equation was in discussion is so that you knew what the stoichiometric ratio is. And so the balanced equation is this. You start out with H3PO3, right? And you add, that's always AQ. You add some water to it, which is liquid, right? And then what you get at the end is the sodium salt of it, which is Na2HPO3 plus 2 waters.
What
Go.
happened to the sodium hydroxide? Like, why isn't that in the?
Oh, just because I screwed up. That's why. I'm sorry. Let me fix that. This is supposed to be sodium hydroxide right here. My bad. There we go. Sorry. Good call. And there's 2 of those. And that's also AQ. There we go. Okay, now that should be the correct balanced equation. That should be the correct balanced equation. All right, so now that we have the correct balanced equation, we know that for every 1 mole of, go ahead. Don't forget that when you have a neutralization reaction, an acid plus a base makes what? Exactly, a salt and water.
A salt and water.
Yes, that's always true. A neutralization reaction always results in a salt and a water.
Okay, thank you.
Okay, so we can see in our completely balanced equation, now that I've corrected it twice, because I wrote it down in the wrong order. But anyway, we can see now that the corrected balanced equation is phosphorus acid plus 2 sodium hydroxides, make you the sodium phosphorus and the 2 waters, okay? What that means then is that we have 1 mole of sodium phosphate for every 2 moles of sodium hydroxide, right? That's what we're looking for, okay? That's what we're looking for. Okay, that's what we're looking for. And so, knowing that, you can say then that 2.38 times 10 to the negative 3 moles of sodium hydroxide, right, can then be used in dimensional analysis to figure out how many moles there was of phosphorus acid. And so down here we have for every 2 moles of sodium hydroxide, like so, right? Which is good because now we can cancel out moles of sodium hydroxide. And then at the top, what do we put? What do we put at the top of that? What are we trying to get to? of, yes, phosphorus acid. So that's 1 mole of phosphorus acid. Like that. See? So the reason why you needed a completely balanced chemical equation here, like Miss Dickens told you, right, in discussion, is because from the balanced equation, you know that for every 1 mole of phosphorus acid, which is in the top row right here of the dimensional analysis, there's 2 moles of sodium hydroxide down here at the bottom of the dimensional analysis, right? So awesomely enough, moles of sodium hydroxide cancel out, and you're left with what? Moles of phosphorus acid. Okay, moles of phosphorus acid. Yes, that's exactly what I got. That is correct. That is exactly what I got. Times 10 to the negative 3, right? Moles of phosphorus acid, right? But now that's just number of moles. We need to get that to concentration. How do we get that to concentration? Well, that was actually given to us in the problem right here. It is a 25 mil sample of phosphorus acid. So you see how you had to pull out 3 or 4 different numbers from that problem, right? So at the very beginning of the problem, it said there's 25 mils, and then concentration is always number of moles over liters, so you can divide all that by 0.025 liters, and that gives you the concentration you're looking for. All right, that'll give you the concentration you're looking for. And again, I put 0.025 liters instead of 25 milliliters because the formula for concentration, molarity, is what? Moles over liters, right? Not moles over milliliters, but moles over liters, right? I heard a wait. What's up?
Wait, can you remind me of something real quick? Why
What?
did you put 0.025 instead of 25? Sorry.
Because the concentration formula, molarity, right, is number of moles over liters, not number of moles over milliliters, right? And I gave you the number of moles, sorry, I gave you the volume in milliliters, so you needed to convert it to liters, which at this point, though, you should be able to do in your head. No, it's okay. At this point, you should be able to do in your head because you're just moving the decimal point 3 places either way, right? You should be able to do that stuff in your head now. All right, so that gives us then the formula, that gives us then the concentration of H3PO3, right, to be, and someone check my math on this, 0.0476 molar. No, that's close enough. That's a rounding error. That's close enough. No, it's okay. No, I mean, you don't know unless I tell you that's a rounding error, right? Yeah, usually if you go out to that many decimal points, right? Like to like the thousands place or even the tens of thousands place, if it's off by 1, that's okay. You're okay about that. You don't have to worry about that so much. I messed up. That's why I'm erasing it right now. Yeah. Yeah. No, it's okay. I just miswrote, so I was trying to erase it so that it wasn't so messy instead of crossing it out. There we go. So it should be molar H3PO3. That's what we should be ending up with. Okay. Okay. Good. Right. So there's the answer to the B right there. What is the concentration in molar? Right. What is the concentration in molar of the phosphorus acid? Okay. And so that was B. So I guess I should write in here which is which. So here's A right here, right? And I erased it, but it is diprotic, right? And then the answer to B is this one. There. Okay. So now we can move on to C, right? Now we can move on to C. The original solution from part B has a pH of 1.59, right? Calculate the percent ionization for just Ka1, right? And the reason why you're doing this is because we know that the very first proton, Ka1, is going to be much larger than Ka2. So that's the one that's going to be the effective proton we're losing, right? And then for the third proton, it doesn't get lost at all because it's not even acidic, okay? Luckily for us, we were given this, the pH of 1.59. What can we use? What can we do with that will give us something that's helpful? Since it's given us the pH, you know that the negative log of the hydronium ion concentration gives you the pH. So to get a hydronium ion concentration, you just have to take the negative log, do the 10 to that, right? Here's C now. And we know from the last lecture that hydronium ion concentration is equal to 10 to the negative pH, right? 10 to the negative pH, okay? Which you are given a pH right here, thank the Lord, right? So all you have to do is say hydronium ion concentration equals 10 to the negative 1.59, okay? And so the hydronium ion concentration should be, and somebody check my math here, it should be 0.026 molar. I think that's what it should be, okay? And remember, I borrowed someone's calculator and showed you on there how to do 10 to the negative, right? There's a little thing there that says 10 to the x, right? You can hit the 10 to the x button, and then just put in negative 1.59 on your calculator, okay? Anybody got a number? You got the same number? Good. Anybody else? All right, so knowing that now, we can actually fill in our ice table. Okay, so here's our ice table. I like how Dr. Pelfrey said, oh, talking about acid-base equilibrium is like ripping the Band-Aid off. But it's more like a slow unwrapping of a suture because it's not very fast, you know? It's not very fast at all. Oh, most of you weren't in here when he said that because he's also teaching acid-base equilibria to his doctorates of nurse anesthesia class right now. And they've been avoiding doing the ice table. So here's our ice table. Okay, so this is the part where Ms. Dickens got confused on Monday, right? And the reason why she got confused is because I wrote up here, we have H3PO3, right? And it can go back and forth. And then what you end up on that side, and normally, right, if you were doing a normal, just single proton equation, right? Single proton equation, it would be this stuff over here on the right-hand side. But it's not, because in the problem, I asked you to only do one Ka, Ka1, right? Not Ka2, not Ka3. So when I say only do one Ka, it means I only want you to remove one proton, right? That one right there. And you're going to ask me, I know someone's going to ask me, how do you know which proton, right? Well, it has to be an acidic proton, number one, right? But number two, both of these are going to be equivalent protons until one gets lost. So it could be either one could be the Ka1, right? So let's just say this top one is the Ka1, and this bottom one here is the Ka2. I only want you to figure out what the Ka1 is. Only one proton. Because it'd be a lot more complicated if I asked you to do two protons. There'd be two ice tables, right? So on the ice table then, we'll draw a line down like that. And then, so what we get then over here is H3O plus, right? And then the conjugate base, which is H2PO3, right? Minus. You see how that's different from what's up here? Because up here, it's HPO3, right? In the completed equation, what is it? HPO3, right? There's only one proton in the completed equation, correct? Right? Right here? In sodium phosphorus, right here, hydrophosphorus, there's only one proton there, right? But down here, what do you have? You've got two protons. The reason why is because I only want you to remove one proton. Okay? You could remove both, but you have to do two ice tables and make this problem much more longer than it needs to be. I will ask you another question like this on an exam that's going to have more than one proton, right? So make sure when you're figuring out what the conjugate base is, if I'm telling you to remove one proton, just Ka1, that you only remove one proton, okay, when you write out the equation. All right, so luckily for us, we've already gone through and done a lot of this math, right, in this ice table. Over here, the first one is the initial of the initial of the phosphorus acid. And so we got that right here. We calculated it right there. That's 0.0476, right? Or 475. Close enough. And then we know that in the initial for the hydronium ion, before any equilibrium occurs, it's 0 and it's 0, right? The other thing that we've already done using all the math, which is great, is that we have gone through and figured out that the hydronium ion concentration, right, is 0.026 right there. That's great because now we can fill that in. We know that the the phosphorus acid lost this much, and then the hydronium ion gained this much. And then we know for every one hydronium ion mole, there's the same number of moles of what? The conjugate base. So that's also going to be a plus 0.026 over there, right? Good stuff, good stuff. So this is something you should probably write down. When someone gives you the pH, like me, the pH will actually give you the hydronium ion concentration, which is actually the what? The equilibrium concentration. So all we have to do now is do the arithmetic, right? Make sure that everything's clear up there. Looks good. We just have to do the arithmetic. This minus this is what? It's going to be 0.022. And then, like I was just saying, put a big star next to this. I gave you the pH. The pH is going to be the equilibrium concentration. Okay? You don't even have to draw out the ice table to know that. If I give you a pH, that's going to be the equilibrium concentration for hydronium. So the answer here is 0.026. And the number here is also going to be 0.026. Okay? And we know that the hydrophosphorus ion here is the same as the hydronium ion because for every one hydronium that's made, also one hydrophosphorus is made. Right? All right. Last step. Well, we're not even done yet. Okay, so all that is done right there. Okay. So we're still looking for the Ka, right? Oh, wait, we're looking for the percent ionization first and then the Ka. So if you remember from the previous slide, a couple of previous slides ago, percent ionization, ion, there, percent ion equals the concentration of hydronium at equilibrium divided by the concentration of the original acid times 100%. Right? Okay. And so all we need to do there is get our hydronium ion concentration, which we found out from the pH, right? Which is here. So that's 0.026 divided by the concentration of the acid, which was we found out here, 0.0476 times 100. And what does that equal? I calculated it to be 55%. Now we'll figure out what Ka is. What is Ka1? And if you recall from the equation, the expression I gave you before, K1 equals exactly the same as it always equals for every single equilibrium thing. It's products divided by what? Reactants. So this is another reason why I had it as H2PO3, because it's going to be H3O plus times H2PO3 minus all over H3PO3, right? I did this math already, and I ran out of room here, so I'm just going to have to squeeze it in. It should be 0.026 times 0.026, all divided by what? What should it be divided by? What? No. Yes, exactly. The equilibrium number from the original. Good job, Stephanie. Divided by 0.022. Because remember, when you get it down to this equation right here, this is called the equilibrium expression right here. The Ka is called the equilibrium expression. So the only numbers that should be going in here are what? The numbers from the equilibrium line of the ice table, right? Does that make sense? Right? Equilibrium expression, numbers only from the equilibrium line. I mean, the only reason why we make an ice table is to get to these numbers down here. Does that make sense? Right? I know this is a long problem. Yes, that is correct. Or you can just make it easy on yourself and say equals 0.031. I don't usually use scientific notation unless it's like to the -7 or something, right? Something that has a crap ton of zeros I don't want to count. But if it's only got a couple zeros, I'm okay with writing it out in what we call float decimal point. Okay? And then so that actually ends all of C. And then the last one, D, it says how does the osmotic pressure of 0.05 molar solution of HCl compare qualitatively, not with numbers, but qualitatively to 0.05 molar solution of phosphorus acid, right? And if you remember back from the solution solution properties lecture, osmotic pressure is all about how many particles that you have in solution that are actually dissolved in the water, right? And we found out from here that the percent ionization of the phosphorus acid, right? Phosphorus acid, which is hard to say sometimes, is only 55%. Okay, so only 55% of the phosphorus acid actually dissolves into the water and becomes particles in the water, right? But what did I say about hydrochloric acid? What kind of acid is hydrochloric acid? So phosphorus acid is a weak acid, right? So it only ionizes 55%. Yes, hydrochloric acid is a strong acid. It ionizes 100% of the time, right? Which means that the osmotic pressure of hydrochloric acid is going to be way higher than the osmotic pressure of phosphorus acid, right? Does that make sense? Because the more protons you have in solution, right, that are actually dissolved in the water, the higher the osmotic pressure. And in this case, for hydrochloric acid, right, in this case for hydrochloric acid, it's going to be 100% versus 100% versus the 55% there. Okay. All right. Any questions on this problem before we move forward? Because osmotic pressure is about having the amount of particles in the solution. Okay, and so what is hydrochloric acid compared to phosphorus acid? It's very strong, which means how much of it will ionize? Pretty much, right? And so if all of the hydrochloric acid is going to ionize, that means it has way more protons in solution than, exactly, way more than the phosphorus acid. And so that's why it's going to have higher osmotic pressure, 55% to the 100%, right, of hydrochloric acid.